All right, and now I can say that we know all of our necessary strategies to do integration. Now we're going to look at some corner cases that we haven't thought of so far. Our bounds have all been finite, right? What if one of our bounds is infinite, or what if both bounds are infinite? That's where improper integrals are going to come in. And so a starting point is we're going to look at just a nice, in quotes, function, 1 over x squared. And we're curious if that is what is going to happen with the area under that curve as we go from 1 to infinity. Is it finite or is it infinite? I mean, you would think it's infinite, right? It goes off to infinity, so how could it be finite? Okay, so if we look at the graph, right, you can pull up Desmos or whatever you need to, but the picture that you're going to get is as it goes to infinity, so starting at 1, right, it's going to be at 1, and then it's going to drop off to 0, or drop off towards 0 quite quickly after that. So it's like, well, okay, well, maybe after some point, area, or when we do a definite integral, we're just adding area. Is the area that we're adding 0? Well, I don't know. Okay, here's what we can do. We don't know how to deal with infinity, but we do know how to deal with limits. What if we did like limit as t approaches infinity of integral 1 to t, and then do dx over x squared? Okay, well, okay, let's rewrite that as x to the minus 2 dx. Okay, we know how to deal with this definite integral, right? So we just have a limit as t rather goes to infinity sticking out front, and then this would be, x to the minus 1 negative evaluated at 1 and t. Okay, so then we get limit as t goes to infinity of negative 1 over t plus 1. Oh, wait, and yeah, I can do the limit of this, right? So the limit of this would just, since it's in the denominator, would just go to 0. So it's just 1. So the area underneath this function from 1 to infinity is just 1. Huh. Okay, what about this one? Change the function a little bit, same idea, right? Still goes towards 0 quickly. Not as quickly as 1 over x squared. All right. So let's try the same strategy. So we're going to do limit as t goes to infinity, integral 1 to t dx over x. This would just be limit as t approaches infinity of, and let's see, that would evaluate to natural log of the absolute value of t, evaluated at 1 and t. Okay, so then this is limit as t goes to infinity of natural log absolute value of, oops, that should have been an x. Yep, that should have been an x. T minus natural log of 1 is 0. So that just goes like that. Oh, but wait. This doesn't exist as a finite number, right? It would diverge. It would go towards infinity. So, I mean, we could write it's infinity, but infinity is a concept, not a number, right? So we're just going to say it doesn't exist as a finite number. So, okay, we got convergence if it was 1 over x squared. We got divergence if it's 1 over x. Okay, and notice the language that I use. If the limit ends up existing as a finite number, we would say it's convergent. If it doesn't exist as a finite number, we'd say it's divergent. Okay, so just to cover that bit of language. Now, when we think about improper integrals of type 1, we've actually done it in kind of one direction. Improper integrals of type 1 start at a finite number and then go from the finite number towards infinity without any breaks in between, any discontinuities, etc. And so this is A is saying the positive case, B is saying the negative case, and then C is kind of looking at both of them. So if both sides of the integration from a constant are convergent, then it's convergent overall. Okay. So there you go. Okay. but a little bit more technicality pieces here. So is if, so this is kind of what we were doing before, is if we can say that the definite integral exists for every t, where t is just going to vary greater than a, then we just say that the improper integral from a to infinity exists and is convergent. Okay. And so here, just to again help visualize, in kind of case A, we begin at A, and here is t, right? Our function is something like this. And so we draw little boundaries, and we're looking at that area. And all we're doing is we're shifting t to the right. Okay? And so if that works for everything, then we're good. Okay? So then for each of these integrals, we'll do a couple together. We're going to look at them and see, does this, if we, bound it from number to t, or t to number, does it exist? And then if it does, slap a limit on it, see what we get for the convergence. Okay, so beginning with this one, I'm going to do equals limit as t approaches infinity, integral 1 to t of natural log of x over x dx. Okay, and you can do u substitutions with these still, so you could let u equal ln x, and then du is equal to dx over x. Okay, and so then you would get limit as something goes to infinity. I am going to still call it t, and then integral ln of x, ln of 1 would be 0, and then I just get ln of t for the upper bound, and then change this to u du. Okay, integrate lim t approaches infinity, u squared over 2, but then I'll write as u squared over 2, evaluated from 0 to natural log of t, and so then this is limit as t goes to infinity of ln of t all squared over 2 and then minus 0, which I'm going to say diverges, right? By similar logic to what we saw above, which diverges. Okay. Next one. Okay, if this one doesn't converge, we probably have done something wrong in our lives. That's an exponential function, right? It's exponential decay. Oh, but we are going from 0 to infinity. Okay, so it should converge, logically speaking, because it decays super fast. So if we do limit t approaches infinity, integral 0 to t e to the negative x dx, integrate that thing. What do we get? Limit t approaches infinity, and then be negative e to the negative x evaluated from 0 to t gives us limit t approaches infinity, negative e to the negative t minus 1. Okay. Now, thinking about the graph, as you go to the right on a negative exponential, it would still go to 0, even if it's that negative out front just flips it vertically. So that's still going to go to 0. And so my final answer is, oh, and I forgot it's a double negative. My bad. That should be 1. Whew, okay. All is right with the world. Next one. Oh man, this looks a little interesting. What do we do with this? Okay, well, we're going to be clever. Okay, but let's just see how clever. All right, so we're going to start with limit as t approaches infinity, and then integral. Wait, why positive infinity? I'll show you why. Negative t to t. Oh, symmetric bounds, and then we have, x squared over 9 plus x squared dx. Okay, and then you're like, oh yeah, there was a property of even functions, x to the sixth, right? This is an even function, so you could actually say that this is 2 times the limit as t approaches infinity, integral 0 to t of x squared over 9 plus x squared dx. 9, 6, I'm going to always mess that one up. Okay. All right, this is fine. How in the world do we integrate this thing? Well, what if we did u is equal to x to the third? Wait, why in the world are you doing that? Well, then du is going to be actually du over 3 is going to be x squared dx. Okay, so I get 2/3 limit t approaches infinity. Oh, the x squared dx. Okay, so worry about bounds in a minute. Let's see, x squared dx. That'd be du. 3 I already brought out. And this would be 9 plus u squared. Oh, that's an arctangent. Yeah. There we go. And then this would be t cubed. Okay. And so specifically, you could go through and do a u sub and all that jazz. What we end up getting at the end of the day is 2/3 times limit as t goes to infinity. We'd have to move the 9 in, which would divide 9 out. So this would be actually 2 over 27. And then we'd have arctangent of u over 3. Let's just call it x cubed over 3. Okay, so I'm doing ... skip some steps, and then evaluate this from 0 to t cubed. Okay, so then what do we get here? 2 over 27, and then limit arctangent of t cubed over 3. Let's see, and then minus arctangent of 0 is 0. Okay, and so then let's see, arctangent, so that's pretty much arctangent of infinity. So where does arctangent go to as it tends towards infinity? That's just pi over 2, and so then I just get pi over 27. Look at that beautiful work. We used symmetry, we used u substitution, and a lot of other algebra in between there. So again, in between steps you might have to work out on your own, but that's the idea. Okay. For improper integrals of type 1, again, we have continuous within the domain of integration, beginning at a point, looking one direction, and going from there. Convergent would be is if we get a number at the end. Otherwise, if the limit does not exist as a finite number, we just say it diverges. All right, and that's going to wrap up the videos for this week.